Thanks for the invitation. I was going to say, Muli randomly calls me twice a year at like 8 a.m. And that's whatever time zone you're in, whatever time zone I'm in. And in this case, it was early in the morning, so you somehow got me to agree. It was just a few weeks ago to come here. Anyway, thanks. It was a good idea. Yes, right. All right. And then yesterday I found out what you told me, that the talks are supposed to be like a survey with some future directions. So then, okay, so that was good to find out. So I'm going to talk about gradient descent, which is probably something that people are familiar with. Let me just remind you what happens in gradient descent. So if you have a convex function on Rn, some Euclidean space, and you want to solve a global minimization problem, gradient descent is a fantastic algorithm. Looks something like this. Move a little bit in the direction of the negative gradient of the function. Do this over and over again. And if your function is convex, this will converge to the minimum. If you want to solve some constrained minimization problem, say you want to minimize your function over a convex body K, then you can do projective gradient descent, which is you do the same gradient descent step where you move in the direction of the negative gradient, but now you have you want to stay inside the body, so you just project back to the body. So here's projective gradient descent, and I'll go say it a little bit later, but once you're willing to do a projection, then actually, to define a projection, one needs some inner product, and if you're willing to use some inner product that varies around the space, then you get what I call regularized gradient descent or Riemannian gradient descent. But this is the kind of algorithm I'm going to talk about. What are the benefits of this algorithm? This is the simplest algorithm that exists in some sense. It's, I guess, all of physics happening around us right now. Some form of gradient descent, but it's very simple. It's robust. It's noise tolerant. If you have noisy gradients, if you can't evaluate the gradient exactly, or if I come along and perturb the position of your algorithm, it still converges. It's like it's phenomenal. It's efficiently implementable in a very strong sense that since it's so stable, many recent algorithmic approaches, even to say classical problems like computing maximum flows, basically set up the problem just as an instance of gradient descent, and then use the fact that you can very cheaply compute something that's a little bit correlated with the gradient and do gradient descent very fast and get very fast algorithms. And one of the sort of contributions of computer science to the world is that convex programs, sort of convex bodies, even simple ones, linear programs, say polytopes, are remarkably expressive, and you can write down lots of fascinating and interesting constraints as convex programs. And if you think about these things long enough, you might have the same experience I had, which is sort of that gradient descent starts to become like a religious experience. In 2016, I taught a class called Entropy Optimality, which is just all about using gradient descent in a variety of areas. And then I also was just, every talk I went to, I would yell at the speaker. Yell is a strong word, but harass the speaker into doing whatever algorithm they were presenting. Basically tell them that's just a form of regularized gradient descent. Okay, you can find this course on my homepage. I think it's really beautiful how much can be represented here, and even things like Christos's talk about the brain. It's very hard to believe that any sufficiently robust algorithm that converges despite defects and noise isn't doing gradient descent in some sense. I guess it's also trivial, sort of in the same way that so let's prove that like say linear programming is p-complete. You can if you allow yourself polynomial time reductions, you can write down any efficient algorithm. You can set up a gradient descent. You can set up a gradient descent instance so that you can essentially simulate any polynomial time algorithm you want. But the religion is in a stronger sense than that there's really some value in understanding things as gradient descent. But like I chose, by the way, this is something Nordic, I guess, just so that I don't know if there are Norsians. Is that what they're called? Norsians? I don't know. Nords. That's what yeah, Nords. Norse. If there are Norsic people here, my apologies if this is offensive. But my point is that like all religions, humans corrupted this one as well. And so in fact, if you go to Google and you search for gradient descent, you will find all kinds of pictures of non-convex functions. Because these days the world is ruled by machine learning, and that's every machine learning person's favorite thing to say, how they're magically optimizing non-convex functions. Okay, and one place this really comes up is a lot is in deep learning. So as a non-expert in deep learning who has, for some reason, gone to a lot of their conferences and workshops and so on, let me give you my perspective on what's happening there, at least in the interesting case. So a lot of times you will see results, for instance, that deep neural networks can do things like linear regression, which is, I mean, linear regression can do linear regression. So that's not maybe so interesting. Let me just, so again, here's my approximation of what, in the non-trivial cases of deep learning, what's happening. So this is some geometry of a convolutional network where the input is an image. In the first layer of the network, you you have these little patches. You have basically a simple function here of the values in some little patch. And then as you move out, here you have a simple function of some, of many of those functions and so on. And the idea here is that in the interesting case, suppose you want to do something, and then by the way, at the end you classify whatever you're seeing, and there's some loss function that comes from your labeled data, and then you use the say each new data point to update the functionality of each of these, well, you can see here, convolution composed with some activation function. But the basic idea is that at the low levels of the neural network, you should be learning basic features. For instance, things like if it's an image, edges, straight lines and so on. And then maybe at the next level of features, you learn the compositions of those things, corners, rounded shapes. And then the features, as you get higher and higher up in the network, you get these higher level features. For instance, maybe recognizing that there's a wheel or a headlight or something. But the idea that makes these things interesting is that the convergence, as low level features converge to something, the higher level features, right? So this helps the higher level features converge. But then it also happens in the other direction as well, meaning that as you, for instance, you can imagine that you start to put straight lines together to get something that approximates a wheel, but then you learn that the feature of seeing a wheel is very important, and that then goes back and helps improve the low-level features, because maybe now once you're interested in a wheel, you realize that you're interested in curves and not maybe polygonal segments. And so I would say that the interesting dynamics of neural networks, when they're really powerful, if I understand what people say there well enough, is this interplay back and forth, where as low-level features improve, it affects the formation of high-level features, and then that helps refine the low-level features, and so on. Okay? And there is, at least, I don't know if the paper is available yet, there is a formal analysis of a process like this by Jeon Alan Zhu and Yuanju Li, where they also show that any kind of kernel-based method would be inefficient, would require some extremely large dimension. And often when you see a picture like this, what's going on? So the point is that if you the loss function here, which basically if you assigns a penalty to incorrectly classifying the input image, is non-convex. I mean, if you average together two pictures of a cat, it's not, it's probably not it's not another cat. It's something else. So I mean, something that you should probably, for its own sake, put down. But yeah, so you right. So then this leads to to people saying that sort of what's happening is this non-convex optimization, and you see these non-convex landscapes, and then you get, as in all corruptions of religion, you get all kinds of stories to explain what's going on that don't necessarily make much sense. And so one of the things I want to say today is just that if you that a procedure like this, an algorithm like this, can arise quite naturally as just a projection of gradient descent in some higher dimensional space. So you might look at some kind of convergence like this where, what seems non-monotone, some, sort of low-level features improve and then high-level features improve, and then that leads to different low-level features and so on as being something that's somewhat unlike gradient descent because it doesn't look monotone. And I just want to, today, what I'm going to tell you is a simple setting coming from the classical field competitive analysis where this kind of thing happens, but what's going on is really just gradient descent in the correct space. Actually, I have one example of that. So here is just, if you take some heat on a surface and do diffusion, the heat spreads out in a nice way. This is a very simple algorithm, right? You literally just, every point just averages itself with its neighbors over and over again. This algorithm is gradient descent. In fact, it's gradient descent on some notion of entropy, but not in an obvious way. Sort of. So it's a sort of famous paper of Jordan, Kinderler, and Otto that heat diffusion is the gradient flow of the entropy on the manifold of measures equipped with basically the Wasserstein metric. So this is just one example where envisioning this process as gradient descent in a high dimensional space leads to a very inefficient algorithm. Say, I mean, that's not how you would want to run the algorithm. The actual algorithm for simulating heat flow, just average with your neighbors, is very fast and very simple. But it has been an incredibly powerful tool to understand this as the projection of a gradient flow in some different space. Okay. Yeah. So that's the conceptual introduction. Now let's go to something more formal. This field of online algorithms. So let me just remind people what the idea is there. You get a sequence of inputs that are arriving online, so they're arriving over time, and at time t, just based on the inputs you've seen so far, your algorithm has to take some action. And that action has some cost, and your goal is to minimize the total cost incurred. And in competitive analysis, the way you analyze the efficacy of such an algorithm is you compare the cost of your algorithm to the cost of the best offline algorithm that sees the entire input sequence in advance. Okay? By the way, the goal is going to be soon to connect the things I said before to this, to a specific problem in this area. And what happens in this setup is that, I mean, basically what the competitive analysis is doing is it's modeling how detrimental uncertainty is on optimization. Right? You're comparing how well you can do optimization online to how well you could have done it if you still the whole input at once. And I have an interesting relationship with this field because my advisor, Christos, who was the first speaker today, just a few years before I became a student, he had written this paper on K-server, which, 2K minus 1 competitive algorithm for K-server, and I tried to understand this algorithm at the time and failed and then I tried to understand it. Later, I had a reading group on, when I became faculty on these things, and the reading group didn't go very well because, yeah, there's this art of designing these algorithms and associated potential functions. It's beautiful, but art is subjective and hard to understand. True. In my defense, by the way, after Subhash's talk, I think the same year I had a reading group on the unique games conjecture and max cut, and Prasad Raghavendra was in the reading group, so like that reading group went better. Okay, so let me tell you just a very simple problem in competitive analysis. So this is MTS on a line. So here's n equally spaced points. The problem is just you can think of if you identify with this robot. Yeah, I kind of do. So yeah, if you were sitting on the line somewhere, and what happens is at every point in time, one of the vertices lights up, and if it lights up under you, you have to move. Okay, so here you don't have to move, here you don't have to move. If it lights up here, the robot has to move. Okay, so maybe okay, so you can see it has to move. The annoying. Right. So then maybe at some, okay, and then yeah, as you can imagine, like eventually you get annoyed and maybe move far away. So the problem is just that you're controlling the robot, and in fact you can easily see here that it suffices to just move left or right one space at a time. That that such algorithms are okay. By the way, your goal here is to minimize the amount that the robot moves. That's what you're trying to do. And yeah, and at every step you just have to make a decision: do you go left or right? And you only have to move if this thing if the input sequence lights up the vertex you're standing on. Okay, that's the MTS problem. Okay, so there's an input sequence, which are these orange dots. Your algorithm has this one constraint that if if the dot comes at position sigma I, then you cannot choose that as your location. The cost of the algorithm is the total distance moved, and it's an online algorithm. If your position at time I is just a function of the inputs you've seen so far. Okay, and here's the sort of what's studied in competitive analysis, the competitive ratio. Your algorithm is alpha competitive if on every input sequence sigma, your cost is at most alpha times the cost of say the best offline algorithm, which is the one sort of the best algorithm in terms of cost if you can see the entire input sequence in advance. And you're allowed to have some additive constant that possibly depends on the number of points. Okay? So the important thing is, like, think about this thing as running for a long amount of time. So yeah, the important thing here is the multiplicative factor. Okay? And there's just one thing. Okay, so if I want to consider randomized algorithms, so the algorithm, the robot now gets to make a random choice, and the only change is that so now the competitive ratio is like sort of we look at the expected cost of the algorithm instead of the cost. Okay? So an algorithm is alpha competitive, its expected cost is at most alpha times the cost of op. Again, op doesn't have to have randomness because it sees the whole input sequence. Okay, so that's so you want to design an algorithm with alpha as small as possible. Everybody's on board? Okay. So let me just mention, the problem has a rich history, and even this simple case, so this problem on a line, the answer is unknown. It's conjectured that the competitive ratio is log n for every metric space, not just for the line, but the conjecture is still unproven. But at least we know, and this is what the best that's known for the line as well, that there's an upper bound of log n squared on the competitive ratio and a lower bound of log n over log n. Okay. All right. So that's what's known. Let me just, in order to sort of write down an algorithm that looks like gradient descent, let me just recast this problem slightly. Okay? I'm going to give you a model that's equivalent, but is simpler to work with. So well, mostly because it's in continuous time. So, so now instead of just having a sort of a position arrive at every point in time, I'm going to have a general cost function. There should be a little plus here. So this is a non-negative cost function. So this is just sort of at every point in time, there's some non-negative cost that comes. And now I'm parameterizing time continuously. This doesn't change the model in a significant way. And instead of a randomized algorithm, I'm just going to look at the distribution of my algorithm at each time. So I'm just going to maintain a probability measure mu t. So instead of having a random variable at time t, I have some probability distribution on the line. And now the equivalent notion of the cost is the okay. So just by the way, like if I had let's see, that's pretty far back. Come on, all right, yeah. So I mean, if I could just charge you cost 1 here instead of requiring you to move, you can see that I would get essentially the same model. So that's what you should be. So okay, so now the notion of cost in this model is just that when the cost function comes, you pay the average cost under your distribution. That's called the service cost, plus the total transportation cost. So if you move, if you change your distribution, you have to pay the cost, like basically the earth mover distance to change your current distribution into the next distribution you want. Okay? And just the point is that this cost model is exactly the same as the one we had before. It's just written in a distributional way. It is in continuous time, but that's not. It's not hard to see if you think about it, as long as that the competitive ratio is the same in both models. But I want to think about this because now it's going to be easier to do gradient descent in the space of mu's. Okay, so is the problem clear? Now I'm going to give an algorithm to solve this problem. Okay, so here's the algorithm. Okay, first I'm going to build I'm going to build like a deep net on the line. It's a convolutional network. So I'm not saying what I'm doing here, but I hope it was clear. I just built a sequence of dyadic approximations to the line with half the number of points at every step, and let me connect them up in a nice convolutional networky way. Here everything looks very symmetric, but it doesn't need to be. You can imagine, every point here should connect to everything within, distance. Like if this is some scale 2 to the I, to all the children within distance order 2 to the I. And also I want to say, by the way, I'm doing this on the line. There's an equivalent for every metric space. There's an equivalent structure. So this is actually going to be there's a variant of this algorithm for every possible metric space. Okay, that's what I want to do. And remember that the state of the algorithm is a distribution, is a probability measure on the points of the line. So I'm going to encode that here as a flow from sort of this unique sink down to unique source down to the sinks. Okay. So like this is a unit flow. I hope it's a unit flow. Somebody help me out. Looks right. Yeah. Okay. And this encodes the probability measure, which is just the measure of the flow at the leaves. It's not a tree, but I'm going to call them leaves because as you saw, like sinks and sources seems harder. Okay, so so that's how we're going to encode a probability measure. And now I want an algorithm. I'm going to describe an algorithm which is just where at every vertex, there's just some local rebalancing of the flow. Okay. Well, I want to think about. So again, every unit flow here gives me some probability distribution on the leaves. That's what I'm playing. Okay. And then at every point in time, a cost function comes down here, and then I want this flow to update according to that cost function. So it has two properties. I don't want to pay very much cost, but also I don't want the probability distribution down here to move very much because I pay movement cost. And so I'm going to describe now an algorithm which just looks like this. Each of at every internal vertex, the children of that vertex are going to report their estimate for the cost they need to play some strategy beneath them. So they're each going to think about them each as agents. If I give this agent 1 unit of probability mass, then it has some strategy, and it's going to report to me what its current estimate is. And then the boss up here is going to look at those estimates and possibly change the way she allocates flow to each of her underlings. Yeah. I was going to say children because it's also a DAG but that's there's child labor laws and things like that. So yeah. So I just want to look at I'm just going to sort of describe a simple algorithm like that. So the point is that the state of this algorithm, this goes on for every internal vertex, but she has 3 children. Okay, sorry, I mixed metaphor, but and she's going to sort of route flow to them, using 3 variables that sum to 1. Okay. Does this make sense? So as you can see, if at every vertex I have a probability distribution on children, that induces a flow. You put 1 unit at the root and then just follow the thing down. You get, that induces a flow to the leaves, and you get a distribution of the leaves. Okay. So first of all, what are the costs everyone is reporting? It's exactly what you would expect. If U, V, and W report these costs, well, of course, all the leaves report the actual cost. The cost function comes down here. They're going to report their actual cost. The internal vertices sort of inductively report costs in the following way. if my children, U, V, and W, report costs CU, CV, and CW, then I'm just going to average the cost under my current distribution. That's the cost I report. This is the most natural thing to do. And so all that's left is to give the dynamics of these variables. How does this agent update its costs in response to remember, there's a cost function coming into leaves. The cost function changes, or doesn't. Maybe the cost function stays constant. But I'm gonna, she's gonna update these Q variables as costs arrive. Okay. And here are the dynamics I'm going to specify. This will make sense, maybe never, but hopefully in a second. The dynamics just look like this. They're basically, I'm going to reduce the weight I put on U multiplicatively, inversely proportional, like scaled according to the negative cost. So basically, I'm going to, if this vertex here is reporting that the cost of playing beneath it is large, I'm going to reduce the weight I put on it accordingly. And then this lambda variable here is just there to you give it whatever value enforces this constraint. Right? So you basically each of these variables reports that each of these vertices reports that there's some cost possibly beneath them. All the these Q values lower, but then there's this constraint has to be satisfied. So whatever lambda value satisfies this constraint, that's what this is. And I didn't say what this is. So basically these dynamics, we're just going to have them run slower the higher up you are in the tree. So h of u is the height of vertex u, and so basically if you think about the scale here as being 2 to the height of u, then everything runs at speed inversely proportional to the scale. Okay, so those are the dynamics. They're not. There's and by the way, this 3 here is related to the fact that there are 3 children. So these dynamics aren't like, they look fairly reasonable. If when I change the values of the flow on these edges, you can think that I'm going to induce possibly, right? If the scale here is like 2 to the h, then when I move a little bit of probability mass over here, I'm going to possibly induce movement at scale 2 to the h below. So it makes sense. Movement is expensive for me, so it makes sense that I'm going to be more hesitant to make changes higher up because that's going to incur more movement in the distribution below. That makes sense. And then this also makes sense if somebody's reporting to me that they're paying a lot of cost, then I'm going to give them less responsibility proportionally.
What about the middle term?
What about the middle term? The
U plus 1/3.
So if you ignore the 1/3, then this is some kind of exponential weight. You're decreasing things exponentially. If you want to think about that intuitively, ignore the 1/3 for a second. You're encoding some memory here. You can think. You may not have seen it from the description of the problem, but you do need to remember what's going on in order to be competitive. You might just be think about the little robot. Could be happily moving along on half the line while this little dot follows it around. But at some point, it would make sense to realize that, for instance, the little dot never moves over here, and so the robot might be like, all right, you get annoyed enough that finally it's like it moves over here, hoping, with the idea that it has to be competitive. So if the optimal solution was sitting over here and paying nothing all this time, then you don't want to miss out on that. So the multiplicative term here, the fact that you're doing you're decreasing this multiplicative, that corresponds to having some memory of the past. The 1/3 is a interesting thing. This is sort of ubiquitous in, say, online algorithms. You can read Cephi's survey on these things. This sort of multiplicative weight with a shift comes up everywhere. When soon I can explain to you why it's there. But let me just say that here are some very simple local dynamics, and if you try to analyze them. Like I said, this problem was studied for a very long time. This algorithm, it turns out, is log n squared competitive. It's the best known, it's even competitive in a stronger sense. It's the best known algorithm for this problem on the line. But if you tried to analyze it, it would be really hard, and you can imagine why. Basically, the dynamics are very complicated. This node is all of these nodes are trying to learn right? They're trying to learn sort of this effective cost, how much they can, and you would hope that that's converging in some sense to the true cost necessarily to play, beneath you. And then, so I'll put, like, if I consider this agent is now making updates based on noisy information reported about the costs below it that may themselves not have converged. So this is a very complicated system of, it's not clear, like, maybe by the time these costs converge to something that represents the true cost, before they converge, maybe this agent is just doing something completely wrong. She's putting all the weight on this subtree when actually there's a very cheap solution over here that she should be playing. And by the time they converge, maybe it's too late because the optimal solution has moved on somewhere else and it's cheaper to play there. This would be hard to analyze. The only reason that we are able to analyze it is that this simple algorithm that was sort of just applying this kind of like local update rule at every step is the shadow of gradient descent in some higher dimensional space. That's actually where the algorithm comes from initially. Okay, so let me explain what I mean by that. So here's a very general setup. This is, you have a convex body K, and at every point in time, you have a vector field that describes how you would like to move inside the body. So the vector field is just, you get to choose that. Sort of, it just expresses your desire for where you would like to, at every point, I would like to be more in some particular direction. And there are natural dynamics given this vector field, which is just to, just to flow along this vector field. So sort of, I get this vector field, maybe, I move according to it. And then a problem comes when I hit the boundary of the convex body. Like if the vector field points outside the body, but I need to stay inside the body, then I have to do something different. Okay, but it makes sense what we're going to do. The natural dynamics are to sort of flow along the vector field and then just project back to the body. Okay, so instead of taking this as my differential equation, I'm going to do this. This is just says this is just a projection of this vector. So in fact, I mean, if you take your vector field and you apply some projection to them, you get some new vector field that always keeps you inside the body, and then you can flow along that. And okay, so it's sort of if you want to think about it just at the most basic level, just think about this as Euclidean projection. So this process is move a little according to the vector field, project back into the body. But it's often useful not to use Euclidean projections, to use some other geometry. And if you really want to have all of the convergence properties that you would have from standard vanilla Euclidean gradient descent, then there's a particular class of projections that have all those properties that are still nice, which are those coming from the Hessians of strictly convex functions. So if you have a strictly convex function phi, this gives you some inner products. So the function is convex if and only if the Hessian is a positive definite. That gives you a positive definite form at every point of the space, so that gives you an inner product. Once you have an inner product, it tells you how you can project. So that gives you some variant of this algorithm. And this, I probably will call it a regularizer, also called a mirror map. But the resulting algorithm has many names because it comes up in many different fields. Mirror descent, this is actually the generic interior point algorithm, gradient flow and information geometry, and so on. And in this setting, with Bubek, Cohen, R.Lee, and Oleg, and Alexander Madry, you can give a closed form for the dynamics of, so basically, given, so the input here to this algorithm is a vector field, which is just like that's my desire in sort of like for how I want to move. So for us, in this setting of competitive analysis, the vectors are just going to be the negative cost function. I'm going to move away from, I'm going to pay less cost. So I'm going to take just actually a constant vector field which points in the direction of the negative cost function. And then to specify the algorithm, the other thing you need is a regularizer, a strictly convex function phi. And then it doesn't matter, you don't have to read this differential equation, but then there's an explicit closed form for the dynamics, assuming some sufficiently nice properties of your of your convex body, and like when I say sufficient and nice, sufficient, they're mild properties of the convex body and the functional phi, and I guess the only other thing you should know is that what this says is just that what you can read off from this differential equation is that the algorithm is just like the resulting algorithm is just doing this flow along the vector field, except that it's experiencing some normal forces from the fact that the boundary of the body is there and it can't leave the boundary of the body. So there's sort of, yes, in fact, any Riemannian metric, you can put any Riemannian metric you want here, and you'll get a similar algorithm. If you want to have nice convergence properties, like you don't get caught in cycles and things, then there is a sense in which these Hessian structures, these metrics coming from the Hessians of convex functions, are the family where you have really nice convergence properties, as if you would have if you just took the flat Euclidean metric. But you're right. I mean, that's exactly. This is just gradient flow on the Riemannian manifold. Okay, it's a. Right, there's a boundary, so yeah, there you have to do projection at the boundary. But this is just, I guess, projected Riemannian flow. That's all that's going on here. And so the point is, yeah. So this. My claim is that this algorithm is actually just of this form. So let me just tell, so the convex body here is here I'm just writing down, this is just a set of all unit flows from the root r here to the leaves. The vector field is just minus the cost function at every point. So it's a natural thing. Like cost is bad, so I want to move I want to move in the direction of minus the cost function. And then, and then what's a little bit tricky to write down correctly is this regularizer. So the function whose Hessian gives me the Riemannian metric. You can read this. What this is, though, this is just if you ignore the 1/3, this is a multi-scale. This is just a multi-scale entropy. So in fact, if you ignore the 1/3 and you ignore this 2 to the h factor, then, well, okay. If this was a tree, it would really be the entropy written according to the train rule. It's not a tree, so it's something else. But it's you can look at it. It looks very similar to an entropy, and so it's just an entropy weighted by scales. Except that it's a noisy entropy. You don't look at the entropy of the of your actual distribution. You apply, you average it with, or you mix it with the uniform distribution at every step. I can say more in a second why this would be the case. But the main point here is that if you do this algorithm, just this, again, it looks complicated because there's a lot of symbols there, but it's like the most basic thing you could possibly do. You literally just move in the direction of negative the cost function, and you have to describe how you deal with the constraints. You have to give a way of projecting when this thing tries to leave the body. But really, it's sort of, you're specifying a convex function specifies the whole algorithm, and my claim is that the dynamics that are induced by this algorithm are exactly these local dynamics I told you before. Okay. And so, one of the main points I'm trying to get across here, I don't know if it's obvious to everyone. When I mention it, for instance, to people doing deep learning, they don't seem to. It doesn't seem that it's something which is immediately intuitive. Is just that sort of this algorithm with sort of these local updates. They actually look a bit strange, and these complicated dynamics. This is just a projection of a gradient flow in the correct space sitting upstairs. Okay, and let me just say that sort of this is a highly souped up version of stuff that has appeared before. It's natural to apply regularization techniques, competitive analysis. But this is pushing it pretty far. Oh yeah, I guess I do want to give credit to my students. I thought actually now Greg Greg Valiant teaches at Stanford this course that Tim Roughgarden started, Modern Algorithmic Toolkit, something like that. Is that the name of it? Yes. So I taught a version of that, and the class project was well, one of the class projects, sort of in lieu of final exam, was that they had to compete against me on this problem, and that's when, like, in sort of these dynamics look pretty simple, but if once I tried to sit down and write them in Python, it was, you know, I had to it's complicated to do general Bregman projections, which is what this algorithm would entail. And in trying to implement the algorithm, you know, trying to hack it together more efficiently, that's the point at which actually, you know, sort of this simple view of the dynamics became clear. So that's just like one of those nice instances that people say sometimes. You try to write down, you try to code something up, and you learn something about what's going on. By the way, I will say it does look like some of this is my algorithm. The students are beating me, but that's because I gave them my algorithm, and they just optimized some of the parameters. So. Okay. So another point that, by the way, what's going on with time? Okay, it will be under that, no problem. Yeah, we'll get done soon. Okay, so what is competitive analysis? It doesn't mean you compete. So oh yeah, no, of course. This was in fact, the only way that they avoided the final exam was to beat me. That was the agreement. What's that? I mean, the thing is, they didn't know. I mean, they should know our incentives were aligned. I didn't want to give a final exam. Yeah. Okay. So the first takeaway message here, I'm going to tie this back to the setting of deep learning and also to the rest of competitive analysis, is just that. Yeah, it's just that you can get these dynamics that look complicated, would be almost impossible to analyze without having this the perspective that this is just some gradient flow. But I didn't tell you why these things are easy to analyze, and this is really the most beautiful thing about this regularized gradient descent algorithm, which is that this whole art of potential functions. So remember, the difficult thing in competitive analysis is that it's hard to capture the structure or characterize the structure of the optimal solution. In fact, it's not even clear exactly what that means. But here the algorithm does it for you in the following sense. So there's what's called the Bregman divergence associated to your regularizer phi. If phi is an entropy, this Bregman divergence is a KL divergence. And so in our setting with this multi-scale entropy, it's like a multi-scale KL divergence. But it has this sort of natural but also beautiful property that you know, as long as this vector field ft, whatever it is, right? This is actually something arbitrary. As long as it's correlated, so remember, like I'm sitting at y, I'm going to try to move in the direction of this vector field, but I won't be able to because it'll leave the body, so I move and then I project. As long as the vector field points in the direction of some point z, from my current point y, I'll be learning about z in the sense that my KL divergence, my KL divergence to z will be getting smaller. So yeah, in this setting of KL divergence, our current solution is like the prior. It's what we expect to happen, and like z is if you think about z as representing opt, then it's sort of the truth, and this is like, you know. So then you can think about this as a measure of how surprised. If I tell you opt, this is how surprised you are that the optimal point is z, given that you're sitting at y. But the main point is that whenever this vector field has information about z, in the sense that it points from y towards z, right, so that this inner product is negative, you're learning about z in the sense that this is decreasing. So in our setting where we're going to take ft to be the cost function, it has this beautiful formulation, which is that for any point z, whenever we're paying more cost than z, we're actually getting closer to z in the sense of KL divergence. In fact, so the point is that, you know, in this setup, the entire algorithm is the phi specifies the algorithm and also gives you the way to analyze it. So in the analysis of this fact is the only way that we ever think of that we think about opt, just through this fact. Like the potential function for relating our performance to opt comes completely here. there is still more work to do because this only bounds the cost that our algorithm pays, and now we also need to bound the movement cost of our algorithm, but that's something completely internal. Our algorithm moves in response to cost, so you can imagine that there's some analysis there. So let me just stress something here which is one of the reasons that people often talk about doing non-convex optimization in an area like deep learning, which is, okay, so like what happens, okay, so humans can drive cars pretty well, so then you train a self-driving car, and then it can drive, I mean, if you, like the Model 3, you can, it's driven me from Seattle to Portland, with minimal intervention, let's say. It's pretty impressive. Yeah, so, okay, so a human can drive a car well. You train a self-driving car, but the solution to the problem might look completely, it might perform as well or better than a human, but the solution might look completely different from the solution a human is employing. And I just want to stress that sort of when you look at convergence in this mode, it's sort of exactly what's going on here. Our algorithm might be doing something completely different from, say, some solution Z. And as long as we're doing just as well on the cost, for instance, so the analog in the learning setting, as long as we're doing just as well on classification error, then we're happy, and we're happy, and like sort of like we might be doing something completely different from what the optimal algorithm is doing, or there's not a unique optimum. That's it's here. But the point is that like there's still an analysis which exactly says that if there's a good solution, so if there's a solution, say with low classification error, either we have classification error that's almost as good, or we're getting closer to that solution. It's a beautiful, simple fact. It's actually extremely powerful.
Doesn't it imply in some sense that there shouldn't be too many good solutions because you cannot get simultaneously close to all of them? So if there were a ton of solutions that all of them are much better than you and all of them are in completely different directions, then something would be.
So no, it doesn't. So for instance, here, okay, I mean, so think about the following. Just, I mean, even on this problem, take the line on endpoints. Just break it into, let's say, square root n regions of, square root n lines of length square root of n, and now just have the cost function be identical on each of them. So now you have root n optimal solutions, and so what's going to happen is basically the same thing that happens oftentimes in deep learning is that your initialization, you will converge to one of those solutions based heavily on your initialization. Right? But that's fine. I mean, if those solutions are far apart, and for instance, if there's a good solution in it, there's never going to be an incentive to switch to a different good solution. So like, you see what I'm...
Yeah, I mean, I see what will happen. I just try to see the analysis. So when you're not converging, before you converge, when your value is bad, and you look at one of the solutions that you're not going to converge to, if you apply this level, you see that you are getting closer to that solution?
So I guess the basic idea is that sort of looks like this. If you, yeah, so let's think about sort of you're in this little, sort of root endpoints, and now you're doing worse than, let's say there's some good solution there, but you're doing worse than that solution. It has to be that you're converging to the good solution there, because as long as you're not paying too much cost, if the algorithm was incentivized to move somewhere else, it would no longer be competitive because now an adversary could get it to keep switching between solutions. So the algorithm here is, okay, I mean, it's basically, I mean, the point is that it's the case that these edges, like these high-level edges, move slowly enough that the algorithm will converge to, the optimal solution on that sub-instance before the high-level edges will want to switch to a different sub-instance. Yeah. Okay, so let me, okay. So, so this is a very powerful framework. For instance, I mean, probably the most impressive application of it is to sort of getting a polylog K competitive algorithm for a K server problem, which is a long-standing open problem in competitive analysis. Okay, let me just now talk about future directions here. So first of all, this algorithm that I described on this convolutional network on the line is only log n squared competitive, and but the conjecture is that you should be able to get a log n competitive algorithm. Actually, the point, the reason it fails to be log n competitive is that, so it really is log n squared competitive. It's not better. Is exactly that it only has one of the properties of, like, the good properties of deep learning, of deep networks that I said. So here it's the case that if you, the sort of, what happens at lower levels doesn't depend on what happens at higher levels. So sort of the flow above this node actually doesn't affect the values on these edges at all. So low level features affect higher level features, but not the other way around. And in fact, it's a big problem. So here's an example. Suppose that my algorithm is sort of playing at this point, and it's represented as a flow like this. And now the cost function is, say, comes at all, a cost function comes which is just large at all these points for a while. So then what should my algorithm do? It makes sense that my algorithm should say, move over here. But it's going to move there quite slowly, because in order to get, it can't get there by doing this. So actually, this edge has to change to here. So like, first this has to happen. So basically, let me say, there's a probability distribution on here, which is just all the masses at this point. This has many representations as a flow. Here are two of them. The green representation is really bad for the algorithm moving one step to the right. Because in order to do that, it has to change these high-level edges that move very slowly. So this is an instance where, so this is what makes the algorithm not log n competitive, but instead log n squared competitive. I don't know how to solve it. If I did, I would be telling you about a better result. But I believe that if you can solve this problem, I like this problem because I don't know if you wanted to analyze, for instance, what's going on in deep networks where you have this give and take, high-level features influence low-level features and vice versa, then here's a nice instance where figuring that out would give a better competitive ratio, where I gave a talk which is online in Copenhagen earlier this year. I think if you can solve this problem, I'm just not going to look at this, but you can get the optimal competitive ratios for a number of long-standing open problems in that area. But more than that, so basically I don't, it's a, if you think about sort of a theory of these hierarchical regularizers, it would be nice to know what's going on here. This is a good test case for figuring out the right thing to do. So that's a great open problem to work on, and if you, and I think it has legs in the sense that it will solve many, many other long-standing open problems. That's so that's the sort of thing in competitive analysis. It would also be nice, and right, so this is, this is what I'm planning to work on in the coming year. It would be really nice to have some non-trivial model of a deep network. So the upcoming paper of Jaewon and Yuan Zhu is a good testing case for that. There, the way that they analyze sort of the dynamics of their neural network is by really, basically, there is a planted solution. So so they know where they want to converge. So they can, they can basically argue that in some sense they can argue that they're converging to that solution. The analysis is quite technical and involved and subtle, and but it really does look like that what they're doing is just a projection of gradient descent in some lifted space. So that would be really beautiful because, gradient descent is robust. So for instance, to all of these. So the point is, like, if you have different activation functions, or you're doing things like dropout, and people have these arguments over which engineering hack makes things better. If you understand things as gradient descent, then of course in gradient descent, all you ever need to do is just make a little bit of, your step has to be a little bit correlated with the gradient, and you're making progress. So that's a great explanation for why, the specific architecture is not necessarily so important. And then once you can do that, you can understand things, for instance, like one of the mysteries in deep learning is why you don't overfit, right? There's this implicit generalization that happens. There's hundreds of papers written about why it happens. a very satisfying perspective on that, again, would be that sort of these deep learning dynamics are just gradient descent in some lifted space. And I guess the last thing I'll just say here is that the connections between, yeah, I mean, I look at sort of some of these problems like MTS and competitive analysis as a nice testing ground. It's not exactly clear why. They're optimizing different things. But let me just mention a little more, just one more sentence about the connection between them. So in learning theory, there's this general idea that models generalize if and only if they're stable. So like that's I mean, you can actually prove that in great generality. And so like movement cost here basically measures stability of one's current solution. Okay? And now you can also look at sort of, yeah, the other aspect of here that seems unrelated possibly to deep learning is that I put these hierarchical weights on the network. Yeah, in the analysis of Jaewan and Yuanzhu, they have to do something similar, which is actually, again, sort of an assumption that's often made, which is to assume that there's something like it's called the information gap between the levels, which is basically the idea that like the low-level features might give you 90% classification accuracy, and then the next level gives you 95%, and the next level gives you 97%, and then 97 point. No, each additional level of features is only eking out a geometrically smaller classification error. That's an assumption they make. I'm not sure. I mean, one of the beautiful things about having a nice model for those things is you might be able to say more. I'm not sure if that's sort of a necessary feature for those kind of dynamics to converge. But that is some relationship between these hierarchical weights in MTS and sort of at least their convergence analysis. Anyway, so it's yeah. So those are some great open problems. Hopefully, some people can solve them.